What if I told you the universe left behind a secret message, one written in faint whispers of light, echoing across billions of years? This isn't science fiction. It's real, stretching across the entire cosmos. There's an ancient glow, a cosmic fingerprint from the dawn of time itself. Scientists call it the cosmic microwave background, or CMB, the afterglow of the Big Bang. It's the oldest light we can see, a snapshot of the universe when it was just a newborn, barely 380,000 years old, and hidden within its subtle patterns lie clues to mysteries so profound they could rewrite everything we think we know about reality. Picture this: you're staring at a map of the sky, but instead of stars, you're seeing the faint remnants of the universe's explosive birth. The CMB is like a time capsule, preserving the conditions of the cosmos in its infancy. But here's the thrilling part: it's not just a relic, it's a riddle. Embedded in that glow are 25 jaw-dropping mysteries that defy explanation. Why does the universe appear lopsided in certain ways? What caused bizarre, unexplained cold spots? Are there hidden dimensions imprinted in this light? Each question is a thread, and pulling on it could unravel the very fabric of our understanding. This isn't just about science, it's about the human spirit of exploration. For decades, the CMB has been our guide, leading us to discoveries that earned Nobel Prizes and reshaped cosmology. Yet, the more we learn, the more the universe seems to whisper, "You're missing something." And that's what makes this journey so electrifying, because these aren't just puzzles for physicists, they're gateways. Gateways to understanding where we came from, what the universe is truly made of, and whether we're alone in the cosmos. So, if you've ever looked up at the night sky and wondered what's out there, buckle up. We're about to dive into the deepest enigmas of the cosmos, and you won't believe what we've found. One of the most baffling puzzles hidden in the cosmic microwave background is something scientists call the horizon problem. Here's the mystery: when we measure the temperature of the CMB across the entire sky, it's almost perfectly uniform down to tiny fractions of a degree. At first glance, that might not sound strange, but think about what this means. Regions of the universe billions of light years apart somehow reached the exact same temperature, as if they'd been in contact. But here's the catch: according to the speed of light, there hasn't been enough time since the Big Bang for heat or energy to travel between these distant regions and balance out. It's like 2 cups of coffee on opposite sides of a freezing room, somehow staying equally hot without ever sharing warmth. So how did the universe pull this off? One leading theory is cosmic inflation, a mind-bending idea that in the first split second after the Big Bang, the universe expanded faster than the speed of light, stretching a tiny, uniform patch of space into the vast cosmos we see today. This would explain the temperature match. Everything was once close enough to equalize before inflation blasted it apart. But inflation isn't a perfect solution. For one, we've never directly observed it happening. It's a mathematical fix to a cosmic riddle. Some researchers argue it's too convenient, like inventing an unseen force just to make the equations work. Others propose wild alternatives, like our universe being just one bubble in an endless multiverse, where collisions between bubbles could leave hidden imprints in the CMB. Yet, even with these theories, the horizon problem lingers. It forces us to question whether we're missing something fundamental about space-time itself. Could gravity work differently on cosmic scales? Is the speed of light not the ultimate speed limit in the early universe? Every time we think we've cracked this puzzle, the CMB seems to whisper back with more questions than answers. And that's what makes it so thrilling, because the universe isn't just handing us solutions, it's daring us to look deeper. Now imagine finding a strange, icy patch in the middle of a warm ocean, an anomaly so glaring it defies the rules. That's essentially what astronomers stumbled upon in the cosmic microwave background, a colossal cold spot stretching over 1 billion light years, where the temperature dips far lower than standard physics predicts. This isn't just a tiny fluctuation. It's a cosmic bruise, a region so unusually frigid that its mere existence sends theorists spiraling into debates about parallel universes, cracks in space-time, or even errors in our most fundamental assumptions. At first glance, the cold spot seems like a statistical fluke, a random quirk in the data, but the odds of it appearing by pure chance are astronomically low, somewhere around 1 in 50. That's like rolling a die 100 times and getting the same improbable number over and over. So what could cause such a bizarre feature? One radical hypothesis suggests this cold spot might be a cosmic collision, an echo of our universe brushing against another bubble universe in a vast multiverse. Picture two soap bubbles barely touching. The energy drain from that contact could leave a chilly imprint in the CMB. It's a mind-blowing idea, but here's the catch. We've never detected direct evidence of other universes, and the math behind this theory is still speculative at best. Another possibility digs into the fabric of spacetime itself. Some theorists argue the cold spot could be a cosmic texture, a rare, not-like defect in the universe's structure, left over from the violent energies of the Big Bang. Think of it like a wrinkle in a bedsheet frozen in time. These textures, if they exist, would warp space around them, subtly altering the CMB's temperature in their vicinity. But again, nobody's ever observed one directly, and simulations struggle to replicate the cold spot's exact properties. Then there's the skeptic's take. Maybe our instruments are playing tricks on us. Could foreground dust in our own galaxy be casting a shadow, mimicking a cold spot? Or is there an undiscovered glitch in how we process the data? After all, the CMB is buried under layers of interference light from stars, gas, and other cosmic clutter. Teasing out its true signal is like listening for a whisper in a hurricane. Yet even after accounting for these factors, the cold spot stubbornly remains, taunting us with its refusal to fit neatly into any box. What makes this mystery so tantalizing is that it refuses to be ignored. Every time we dismiss it as noise, it resurfaces in new observations, slightly changed but undeniably present. It's a cosmic Rorschach test, revealing as much about our theories as it does about the universe. Are we staring at the footprint of another reality, or just a blind spot in our understanding? The answer, whatever it is, could rewrite the rules of cosmology, and that's the beauty of the cold spot. It doesn't just challenge what we know, it dares us to imagine what we've missed. The universe has a way of surprising us. Just when we think we've figured out its rules, it throws a curveball. And one of the biggest curveballs hidden in the cosmic microwave background is something called the missing large-scale anisotropies. Here's the puzzle. When scientists mapped the CMB's temperature variations, they expected to see a certain level of fluctuation wrinkles in space-time across vast distances. But on the largest scales, the universe appears suspiciously smooth. It's like expecting a stormy ocean and instead finding a glassy pond stretching farther than the eye can see. This isn't just a minor discrepancy. It's a full-blown cosmic contradiction, defying what our best models of the universe predict. So why does this matter? Think of the CMB as a fossil record of the early universe. Those temperature fluctuations are imprints of tiny density variations, seeds that eventually grew into galaxies, clusters, and the cosmic web we see today. According to the standard model of cosmology, gravity should have amplified these wrinkles over time, leaving a distinct pattern of anisotropies at all scales. But when we look at the biggest patches of the sky, the fluctuations are eerily muted. It's as if someone took sandpaper to the universe's blueprint, smoothing out the very structures that should be there. This anomaly has sent theorists scrambling for explanations. One possibility is that our understanding of gravity is incomplete. Einstein's theory of general relativity has been tested relentlessly, and it works astonishingly well, but what if it breaks down on cosmic scales? Some researchers propose modified gravity theories where the force behaves differently over immense distances. Imagine gravity as a river. On small scales, it flows predictably, but over vast stretches, its currents might change in ways we don't yet understand. If true, this could explain why the universe's largest structures aren't as clumpy as expected. Then there's the dark energy angle. This mysterious force driving the universe's accelerated expansion might not be as uniform as we thought. Could pockets of exotic dark energy be suppressing those large-scale anisotropies like an invisible hand smoothing out cosmic wrinkles? Or perhaps the answer lies in something even stranger, like the universe being finite, but wrapped in on itself in a way that limits how large structures can form. Picture a video game where the map loops back around. If you travel far enough, you end up where you started. In such a universe, the largest possible fluctuations might never have room to fully develop. But here's the twist. Every proposed solution comes with its own set of headaches. Modified gravity has trouble explaining other observations without breaking something else. Exotic dark energy lacks direct evidence, and a finite universe that contradicts other measurements suggesting the cosmos is infinite. The missing anisotropies aren't just a gap in our knowledge, they're a flashing neon sign pointing to something fundamental we're missing. What makes this mystery so electrifying is that it's not just about fixing a glitch in the equations. It's about confronting the possibility that our entire cosmic framework, gravity, dark energy, the shape of spacetime, might need rethinking. The CMB isn't just a relic of the past, it's a mirror reflecting our blind spots. And until we solve this puzzle, the universe will keep whispering a tantalizing question: what else don't we know? Among all the cosmic mysteries lurking in the cosmic microwave background, few are as unsettling or as fittingly named as the axis of evil. This isn't some apocalyptic prophecy, but a spine-tingling anomaly. Certain patterns in the CMB's temperature fluctuations appear eerily aligned with the plane of our solar system. It's as if the universe's oldest light is whispering, "You're not just observing, you're part of the story." And that's a problem, because in cosmology we assume we're unbiased observers, not central players. So why does the cosmos seem to care which way Earth is tilted? The axis of evil first raised eyebrows when researchers noticed something peculiar in the data. The CMB's so-called multipole moments, essentially its large-scale hot and cold spots, weren't distributed randomly across the sky as theory predicted. Instead, they showed a strange preference clustering along an axis that suspiciously lines up with our solar system's ecliptic plane. Imagine throwing confetti in the air, only to watch it arrange itself into arrows pointing at your feet. Statistically, the odds of this happening by chance are slim, somewhere around 1 in 1,000. That's not quite lottery-winning improbable, but for scientists who stake their careers on cosmic randomness, it's enough to trigger a full-blown identity crisis. Could this be a fluke, perhaps, but the more we analyze the data, the harder it becomes to dismiss. Some researchers argue it's an artifact of measurement errors or foreground interference, like our own galaxy's dust cloud casting a subtle shadow. Others suspect more insidious biases, like the way we process CMB data, or even the instruments themselves subtly imprinting their orientation onto the results. It's the cosmic equivalent of a photographer accidentally including their thumb in every shot. But here's where it gets wild. If the axis of evil isn't a mistake, it could mean our solar system occupies a disturbingly special place in the universe, a throwback to pre-Copernican thinking where Earth sat at the center of everything. Modern cosmology rejects such hubris, yet the data keeps taunting us. One radical theory suggests the anomaly might hint at a pre-Big Bang structure, some primordial asymmetry frozen into spacetime itself. Picture the universe like a cracked mirror with our solar system sitting along one of its fractures. Then there's the quantum angle. Could the act of observing the CMB somehow influence its properties, tying the universe's ancient light to our local environment? It's a stretch, but not impossible. Quantum mechanics has shown that measurement can alter reality at tiny scales. maybe, just maybe, there's an undiscovered law linking the observer to the observed across cosmic time. The axis of evil isn't just a curiosity, it's a confrontation, a challenge to our most cherished assumptions about the universe's uniformity and our place within it. Solve this and we might unlock secrets about the cosmos's true nature, ignore it, and risk building our theories on a foundation of blind spots. Either way, one thing's certain, the universe has a wicked sense of humor. Deep in the shadows of the cosmic microwave background lurk two anomalies so peculiar, they've left cosmologists scratching their heads: the quadrupole and octupole moments. These terms might sound like something from a sci-fi novel, but they're actually mathematical descriptors for how the CMB's temperature varies across different scales. The quadrupole captures variations over 90 degrees on the sky, while the octupole zooms in on 60 degrees. And here's the kicker: both show strikingly less power than our theories predict. It's as if the universe turned down the volume on these cosmic frequencies, leaving us with a signal so faint it barely registers. Why does this matter? Imagine you're tuning a radio expecting to hear a symphony, only to find certain notes mysteriously muted. That's essentially what's happening here. The universe's opening act isn't playing by the rules. Standard cosmology says these multipole moments should be stronger, shaped by the same primordial density fluctuations that seeded galaxies, but the data tells a different story. Some researchers argue this could be evidence of a finite universe, one that's smaller than we thought, with a topology so curved it literally dampens these large-scale vibrations. Picture a guitar string, pluck it short and the note is higher, stretch it across infinite space and the tone deepens. If the universe is small, certain cosmic harmonics might simply vanish. Then there's the anisotropy angle. Could the universe itself be fundamentally lopsided, with properties that change depending on which direction you look? It sounds radical, but the quadrupole and octupole alignments hint at this possibility. If true, it would mean the Big Bang didn't create a perfectly uniform cosmos, it left behind a subtle tilt, like a painting hanging crooked on the wall. But before we rewrite the textbooks, there's the skeptic's take. Maybe our instruments are to blame. The Planck satellite, which mapped the CMB in exquisite detail, had to subtract foreground noise from our own Milky Way. Could imperfections in that process have accidentally erased these multipole signals? Or perhaps the anomalies are statistical ghosts, flukes that'll vanish with better data. After all, the universe only gives us one CMB to observe, and teasing truth from noise is like reconstructing a symphony from a single, crackly recording. Yet the plot thickens. These anomalies don't exist in isolation. The quadrupole's weak power also aligns suspiciously with the so-called axis of evil, as if the cosmos is pointing us toward something deeper. Could this be a clue to undiscovered physics, a relic of pre-inflationary conditions, or even evidence of a sibling universe bumping against ours in the multiverse? The quadrupole and octupole mysteries are more than just data quirks. They're cosmic breadcrumbs leading us toward questions about the universe's shape, size, and very origins. And until we solve them, we're left with a humbling truth. The universe might not just be stranger than we imagine, it could be stranger than we can imagine. There's something deeply unsettling about the cosmic microwave background's hemispherical asymmetry, a cosmic seesaw where one half of the sky seems subtly but undeniably different from the other. Imagine splitting the universe down the middle and discovering that one side is ever so slightly warmer, its temperature fluctuations more pronounced while the other feels oddly muted. This isn't just a minor glitch in the data, it's a full-blown cosmic anomaly challenging our assumption that the universe should look the same in every direction. The numbers don't lie. When researchers divided the CMB map into northern and southern hemispheres, they found discrepancies in both temperature and fluctuation strength. The northern half appears slightly hotter, with more vigorous variations, while the southern half is cooler and smoother. Statistically, the odds of this happening by random chance are less than 1 in 1,000. That's like flipping a coin 100 times and getting heads 90 times in a row. Something's clearly off. But what? One possibility is primordial inhomogeneity, a relic from the universe's earliest moments. If the Big Bang didn't produce a perfectly uniform soup of matter and energy, tiny imbalances could have snowballed over billions of years, leaving one hemisphere slightly more energetic than the other. Think of it like a baker kneading dough unevenly. Some pockets end up denser, others airier, even if the recipe was supposed to be consistent. But here's the catch: inflation theory, our leading explanation for the universe's smoothness, demands near-perfect uniformity. If the CMB's asymmetry is real, it could mean inflation wasn't the flawless process we've assumed. Maybe it started late in some regions or fizzled out prematurely, leaving behind a lopsided cosmos. Then there's the observational elephant in the room. Could this asymmetry be a trick of perspective? Our solar system isn't stationary. It's hurtling through space at over 1 million miles per hour relative to the CMB. That motion creates a Doppler effect, slightly blue-shifting light in the direction we're moving and red-shifting it behind us. Scientists account for this, but what if there's an unseen foreground contaminant, a veil of dust or an ancient magnetic field skewing our measurements? It's like trying to read a billboard through fog. The message might be distorted without us realizing, but the plot thickens. The asymmetry's axis suspiciously aligns with other CMB anomalies, the axis of evil, the quadrupole, as if the universe is pointing us toward a single, unexplained phenomenon. Some theorists speculate this could hint at a pre-inflationary structure, a scar from whatever birthed the Big Bang itself. Others float even wilder ideas, like our universe being a collision zone between two bubble universes, leaving one side subtly altered. What makes this asymmetry so haunting isn't just its defiance of expectations. It's the nagging possibility that we're seeing the universe through a keyhole, missing a larger picture where asymmetry isn't a flaw but a feature. Until we crack this code, the CMB's lopsided whisper will keep tugging at cosmology's foundation, reminding us that the universe owes us neither symmetry nor simplicity. If the universe had a previous incarnation, a cycle of death and rebirth stretching back before the Big Bang, how would we know? Some cosmologists argue the answer lies in the cosmic microwave background. Certain cyclic universe models predict that if our cosmos was born from the collision of higher dimensional membranes, or brains, the event should have left behind telltale circular patterns, cosmic bruises where these titanic structures smashed together. These rings would stretch across the sky, subtle but unmistakable fingerprints of a universe with a past life. But here's the catch: when scientists combed through the CMB's intricate tapestry, searching for these colossal imprints, they found nothing. The sky isn't whispering about previous cycles, it's silent. This absence isn't just a minor setback, it's a potential death blow for some alternative cosmologies. The idea of a cyclic universe is elegant. Instead of a singular Big Bang, space and time could be caught in an endless loop: expansion, contraction, collision, rebirth. Each cycle would reset the cosmic clock, but not perfectly. Like ripples in a pond after a stone is tossed, each bounce should leave residual echoes in the CMB, particularly as concentric rings where temperatures vary in precise, repeating intervals. Finding these rings would be like uncovering fossilized footprints of a pre-Big Bang era. Yet the data tells a different story. Meticulous searches by teams using the Planck satellite and other instruments have turned up empty-handed. Not a single statistically significant giant ring exists in the CMB's fluctuations. The patterns these models demand simply aren't there. It's as if detectives arrived at a crime scene expecting blood spatter, only to find the walls spotless. What makes this silence so deafening is the stakes. Cyclic models aren't just quirky alternatives, they're attempts to solve some of cosmology's deepest puzzles, like what preceded the Big Bang or why the universe's entropy appears finely tuned. Without those giant rings, these theories lose their smoking gun. Some researchers cling to hope, suggesting the rings might be fainter than we can detect or masked by foreground noise. Others argue the models themselves need tweaking. Perhaps collisions leave subtler imprints, or the cycles work differently than we imagined. But the longer the CMB refuses to cooperate, the more it pushes cosmologists toward a sobering realization. Maybe the universe isn't cyclic at all. Maybe time has a true beginning with no before to speak of. If so, the lack of giant rings isn't just an observational quirk, it's a boundary, a line drawn by nature itself. Beyond it lies not another cycle, but the ultimate unknown, and that's the real mystery. The CMB isn't just a relic of the universe's birth. It's a mirror reflecting not only what happened, but what didn't. When scientists first mapped the cosmic microwave background, they expected its tiny temperature fluctuations to follow a predictable pattern, one governed by Gaussian statistics. That term might sound technical, but it's essentially the universe playing dice. In a perfectly Gaussian CMB, hot and cold spots would be distributed like the results of rolling a fair die, mostly small, random variations with extreme outliers vanishingly rare. But what if the universe isn't playing fair? Hidden in the CMB's subtle wrinkles, some researchers believe they've spotted faint hints of non-Gaussianity deviations so slight they're barely perceptible, yet potentially revolutionary. Why does this matter? Imagine inflation. The universe's explosive early growth spurt as a stretchy canvas. Most theories assume it expanded smoothly, leaving behind Gaussian fluctuations like random brushstrokes. But if the CMB shows even subtle non-Gaussianity, it could mean inflation wasn't a uniform process. Perhaps it happened in fits and starts, with quantum fields interacting in ways that left behind clusters of irregularities like bunched-up threads in fabric. These anomalies would be whispers from the universe's first trillionth of a second, clues about forces we've never directly observed. The search for these deviations has been a roller coaster. Early data from the WMAP satellite sparked excitement with tentative signs of non-Gaussianity, but the higher resolution Planck mission later tempered those hopes. Its findings leaned Gaussian mostly. There are still curious glitches, like a handful of unusually large cold spots that might hint at something deeper. But here's the catch: distinguishing true non-Gaussianity from cosmic variance or measurement noise is like listening for a single off-key note in a symphony performed by an orchestra of trillions. Some theorists argue we're missing the forest for the trees. Certain inflation models, like those involving multiple interacting fields, predict subtle non-Gaussianity. If it's there but too faint for current telescopes, future observatories like the proposed CMB S4 project could finally spot it. Others propose more radical ideas, like the universe being born from a collision of higher dimensional brains, which would leave distinctly non-Gaussian fingerprints. But skeptics warn against seeing patterns where none exist. The CMB is a noisy relic, and humans are pattern-seeking creatures. Without incontrovertible evidence, non-Gaussianity remains a tantalizing what if. Yet that uncertainty is precisely what makes this debate so thrilling. Because if the deviations are real, they're not just statistical quirks, they're cracks in the foundation of modern cosmology waiting to be pried open. The universe is supposed to be expanding uniformly, like raisins in rising dough, each galaxy cluster drifting apart as space itself stretches. But in 2008, astronomers made a jaw-dropping claim. Hundreds of galaxy clusters aren't just moving outward, they're being pulled in the same direction at breakneck speeds, as if something massive beyond the edge of our observable universe is yanking them. They called it dark flow, and if it's real, it's not just a mystery, it's a revolution. Here's how the discovery unfolded. Scientists were studying the cosmic microwave background's subtle distortions caused by galaxy clusters racing through space. These distortions, known as the kinematic Sunyaev-Zeldovich effect, act like cosmic speedometers, revealing how fast clusters are moving relative to the CMB's rest frame. But when researchers analyzed data from over 700 clusters, they found something bizarre. Instead of random motion, these clusters showed a coordinated drift toward a single patch of sky near the constellations Centaurus and Vela, a flow so vast it defied explanation. The implications are staggering. According to standard cosmology, nothing beyond the observable universe should affect us. Its light hasn't had time to reach us since the Big Bang. Yet dark flow suggests the gravitational pull of something immense out there, perhaps a supercluster of matter left over from an earlier phase of the cosmos, or even a neighboring universe brushing against ours in the multiverse. Picture a ship at sea tugged by an invisible current, hinting at land just beyond the horizon. But not everyone's convinced. Skeptics argue the signal could be an artifact of incomplete data or systematic errors in how we subtract foreground noise from the CMB. Others point to the Planck satellite's later analysis, which found no significant evidence of dark flow, though some researchers counter that Planck's methodology might have smoothed over the very signal they sought. It's a classic cosmic detective story. One team claims a breakthrough, another calls it a mirage. What makes dark flow so electrifying isn't just the debate, it's the stakes. If real, it shatters the assumption that the observable universe is all we can ever know. If false, it's a cautionary tale about how even our best instruments can deceive us. Either way, the mystery lingers like a shadow at the edge of the cosmos, daring us to look deeper, because sometimes the universe's most profound secrets aren't in the light, they're in the tug of the unseen. If you thought the cosmic microwave background had given up all its secrets, think again. One of its most tantalizing puzzles lies not in temperature variations, but in light's hidden dance, its polarization. Scientists have long hunted for a specific twist in this dance called primordial B-mode polarization, a subtle swirling pattern that would be the smoking gun for cosmic inflation. These spirals, if they exist, would be the fingerprints of gravitational waves rippling through the infant universe, stretching space-time itself during its explosive first moments. But here's the catch: despite decades of searching, the CMB refuses to show its hand. The B-modes remain missing, and their absence is sending shockwaves through cosmology. To understand why this matters, picture tossing a pebble into a pond. The ripples that spread outward are like gravitational waves, distortions in the fabric of reality. Inflation theory predicts these waves would have been so powerful in the universe's first fraction of a second that they'd leave permanent curls in the CMB's polarization. Finding those curls would confirm inflation happened almost beyond doubt. But after missions like BICEP, Planck, and the South Pole Telescope sifted through the data with painstaking precision, the universe offered only silence. The primordial B-modes simply aren't there, or if they are, they're so faint they've vanished into the noise. This leaves theorists at a crossroads. Some argue inflation might have been weaker than we thought, producing gravitational waves too feeble to detect. Others propose more exotic scenarios like inflation happening in fits and starts, or multiple phases where early waves got erased. There's even a radical idea called no-slowness inflation, where the universe's expansion was so rapid it barely left a gravitational trace. But each of these fixes comes with trade-offs, forcing scientists to question whether inflation's simplest, most elegant versions are already ruled out. Then there's the elephant in the room. Are we even looking for the right signal? The CMB is buried under layers of interference, dust in our galaxy, synchrotron radiation, and other cosmic static, all of which can mimic B-modes. Teams like BICEP famously thought they'd found them in 2014, only to realize galactic dust had fooled them. This isn't just a technical hurdle, it's a cosmic shell game where the universe hides the truth behind celestial noise. But the most unsettling possibility is that the missing B-modes aren't a fluke, they're a message. Inflation might not be the only game in town. alternative theories like bouncing cosmologies or emergent universes don't predict primordial gravitational waves at all. If these models are correct, the silence isn't a failure. It's a signpost pointing to something entirely different. What makes this search so gripping isn't just what we might find, but what we've already learned by not finding it. The absence of B-modes has pushed cosmology to its limits, forcing us to question whether we've been telling the right story about the universe's birth. And until those elusive spirals appear, or definitively don't, every quiet observation speaks volumes. The cosmic microwave background doesn't just preserve the universe's infancy, it also holds clues to its turbulent adolescence. One of the most enigmatic chapters in that story is the era of reionization, a cosmic dawn when the first stars and galaxies ignited, flooding space with enough ultraviolet radiation to rip electrons from atoms. This marked the end of the universe's so-called Dark Ages, transforming it from a neutral fog into the transparent cosmos we see today. But here's the puzzle. The CMB's polarization patterns suggest this awakening happened surprisingly late, hundreds of millions of years after the Big Bang. Why did the universe hit the snooze button? To understand the mystery, picture the early cosmos as a vast, cold sea of hydrogen gas. After the CMB's release, space was dark and neutral until the first stars flickered on, their fierce UV light ionizing the surrounding gas like a match touched to paper. Over time, these ionized bubbles grew and merged, a process we can trace through the CMB's polarized light. When this ancient radiation passed through ionized gas, electrons scattered its photons, imprinting a distinct swirl in their polarization, a record of when and how quickly reionization unfolded. Yet when scientists compared this fingerprint to theoretical predictions, something didn't add up. The data points to reionization beginning around redshift 15, much later than some simulations anticipated. What stalled the cosmos's coming of age? One possibility lies in the stars themselves. Early models assumed the first stars were massive, short-lived giants, pumping out UV radiation like cosmic lighthouses. But if those stars were rarer or less efficient at ionizing than we thought, perhaps shrouded in dense gas clouds that absorbed their light, reionization could have sputtered along at a slower pace. Alternatively, maybe the universe's early galaxies were smaller and dimmer, their light struggling to pierce the primordial fog. There's even a wild card: what if dark matter played a role? Some theories suggest certain types of dark matter particles could have suppressed early star formation by cooling gas too efficiently, delaying the dawn of light. Then there's the observational challenge. Studying reionization is like reconstructing a fireworks display from the ashes it left behind. The CMB gives us the broad strokes, but finer details come from quasars, distant beacons whose light, absorbed by neutral hydrogen, reveals the timeline of clearing fog. The catch: quasars are rare in the early universe, and their data hints at a patchy, uneven reionization. Some regions may have ionized early while others lingered in darkness, creating a cosmic mosaic that defies simple models. The reionization puzzle isn't just about timing, it's a window into the universe's first structures. Solve it, and we'll know what those pioneering stars and galaxies were really like. Until then, the CMB's polarized whispers remind us, even in its adolescence, the universe was full of surprises. Every rainbow hides a secret, and the cosmic microwave background spectrum is no exception. On the surface, it's nearly a perfect blackbody, the thermal echo of a universe once scorching hot, and now cooled to just 2.7 degrees above absolute zero. But buried in that smooth curve are tiny, stubborn deviations, spectral distortions so faint they're like finding a single misplaced pixel in a billion. These anomalies shouldn't exist, yet they do, and they might be whispering about cataclysmic events in the cosmos's first chapters: particles vanishing into darkness, or bursts of energy so violent they left scars on light itself. Take the so-called mu distortion, a subtle bump in the CMB's spectrum around certain frequencies. This glitch could be the ghost of an ancient energy injection, a moment when the young universe was suddenly flooded with extra heat, perhaps from the death throes of exotic particles or the collapse of cosmic strings. Imagine throwing a rock into a still pond. The ripples distort the surface briefly before fading. The mu distortion is like that ripple frozen in time. If confirmed, it would mean the universe wasn't just cooling passively after the Big Bang. Something happened, something dramatic enough to leave a mark. Then there's the Y distortion, a broader spectral tilt linked to later eras. This one's thought to come from the reionization epoch, when the first stars and galaxies reheated the cosmos, scattering CMB photons through hot electron gas like light through a prism. But here's the twist: the Y signature we see doesn't quite match predictions. It's too strong in some places, too weak in others, as if the universe's teenage rebellion was even wilder than we thought. The real thriller, though, is the excess at certain wavelengths, hints of extra photons where none should be. Some theorists wonder if these could be the last breaths of dark matter particles decaying into radiation. Others propose more radical ideas, like primordial black holes evaporating in a flash of Hawking radiation, or even echoes of a pre-Big Bang phase. It's detective work at the quantum level, where every anomaly is a clue, and every clue points to physics beyond our textbooks. Yet proving any of this is like trying to hear a whisper in a thunderstorm. The CMB spectrum is buried under foreground noise, dust, starlight, even our own galaxy's magnetic field. Teasing out true distortions requires instruments of insane precision, like the proposed PIXI mission, which could measure temperature variations 100 million times smaller than those NASA COBE satellite detected in the 1990s. What makes these spectral ghosts so compelling isn't just their existence, it's their defiance. They refuse to fit neatly into our models, nudging us toward darker, richer possibilities. Maybe the early universe wasn't just a smooth expansion, but a battlefield of exotic physics. Maybe dark matter isn't just invisible, it's active, decaying or colliding in ways we've yet to imagine. Or perhaps the anomalies are just cosmic mirages, tricks of the light waiting to be dissolved by better data. But until we know, the CMB's imperfect spectrum remains a tantalizing cipher, one that could rewrite not just our past, but our understanding of reality itself. The universe is a meticulous chemist, or at least it should be. When scientists recreated the conditions of the Big Bang in equations, they found a recipe for the cosmos's first elements: hydrogen, helium, and a dash of lithium. These light elements forged in the fiery minutes after creation should have left traces we can still measure today, and for the most part they do. Helium checks out. Deuterium, spot on, but lithium, that's where the cosmic math breaks down. According to the CMB's calculations, there should be about 3 times more lithium-7 in the universe than what we actually observe in ancient stars. This isn't a minor rounding error. It's a gaping hole in our understanding of nuclear physics, cosmology, or both. So where did the lithium go? One possibility is that our models of stellar interiors are missing something. The oldest stars, known as population Roman II stars, act like cosmic time capsules, preserving the pristine element mix from the early universe. But if these stars have been quietly destroying lithium over billions of years, say, by dragging it into their cores and fusing it away, that could explain the deficit. Think of it like a sink draining water. If you only measure what's left in the basin, you might not realize some trickled down the pipes. The problem. Current stellar physics struggles to explain how stars could consume that much lithium without leaving other imprints we'd easily spot. Then there's the nuclear physics angle. The rates at which protons and neutrons fused in the primordial soup, a process called Big Bang nucleosynthesis, are calculated with precision. But what if unknown particles or forces messed with those reactions? Some theories propose that certain types of dark matter could have disrupted the delicate nuclear dance, skewing lithium production. Imagine baking a cake where an unseen hand keeps nudging the oven dial. The final product might not match the recipe. But the most radical solutions rewrite cosmology itself. Maybe the early universe wasn't as uniform as we think. If pockets of space had slightly different densities or temperatures, lithium could have formed unevenly, leaving some regions starved. Or perhaps the CMB's snapshot of the early cosmos hides surprises like an unexpected shift in the neutron-to-proton ratio that threw off nucleosynthesis. These ideas tread dangerously close to heresy, challenging the bedrock assumption that the universe's initial conditions were as smooth as the CMB suggests. The lithium problem isn't just a quirk of astrophysics, it's a flare in the dark, signaling that something fundamental is missing from our cosmic story. Until we solve it, every calculation about the universe's birth comes with an asterisk, a reminder that even the oldest light might not be telling us everything. One of the biggest headaches in modern cosmology goes by a deceptively simple name: the Hubble tension. At its core, it's a numbers game. How fast is the universe expanding right now? You'd think we'd have a straightforward answer, but here's the rub. When scientists calculate this rate, called the Hubble constant, using the cosmic microwave background, they get one number. But when they measure it by observing nearby galaxies and supernova, they get a different number, and these aren't just tiny discrepancies we can shrug off. We're talking about a gap big enough to throw cosmology into chaos. The CMB method pegs the expansion at around 67 kilometers per second per megaparsec, while local measurements consistently land near 73. That's not a rounding error, it's a full-blown crisis. So why should we care? Because this tension isn't just about abstract math. It's a potential crack in the foundation of our understanding of the universe. The CMB's value comes from extrapolating backward, using the physics of the early cosmos to predict today's expansion. It's like rewinding a film and assuming the playback speed never changes. Meanwhile, local measurements like tracking the distances and speeds of pulsating stars called cepheids or the brightness of exploding supernovae give us a direct snapshot of the present. Both methods are painstakingly precise, yet they refuse to agree. It's as if your GPS and your car's odometer insisted you were on two different roads at the same time. Theories abound to explain this rift. One tantalizing possibility is that dark energy, the mysterious force accelerating the universe's expansion, isn't constant after all. Maybe it's growing stronger over time, throwing off our CMB predictions. Or perhaps there's an unknown particle, like a dark radiation, subtly altering the early universe's energy balance. Some even speculate that our corner of the cosmos sits in a peculiar void, a low-density bubble distorting local measurements. But before we rewrite physics, there's the skeptic's take. What if we're just measuring wrong? Cepheids and supernova rely on complex distance ladders, where each rung introduces potential errors. Even the CMB's pristine data has assumptions baked in, like the exact nature of primordial fluctuations. Could overlooked biases be tilting the scales? Teams have triple-checked refined instruments, and still the tension holds. That stubbornness is what makes this so thrilling. The Hubble tension isn't just a puzzle, it's a provocation. Either we've missed something basic in our cosmic yardsticks, or the universe is hiding a surprise behind the curtain. And until we solve it, every textbook on cosmology comes with an asterisk, subject to change without notice. Dark energy was supposed to be simple, an unchanging force woven into the fabric of space itself, gently pushing the universe apart at an ever-increasing rate. That's what Einstein's cosmological constant suggested, a static, predictable driver of cosmic acceleration. But the cosmic microwave background is dropping hints that dark energy might be far stranger, a shapeshifter whose strength could be evolving over time, rewriting the universe's expiration date in the process. Buried in the CMB's subtle patterns are clues about dark energy's equation of state, a fancy term for how its pressure relates to its density. If dark energy behaves like a true cosmological constant, this value should be exactly -1, a fixed fingerprint across cosmic history. But when scientists combine CMB data with measurements of galaxy clusters and supernova, the numbers wobble. Some analyses suggest dark energy's equation of state might deviate ever so slightly from that expected value, as if the force isn't constant after all. It's like discovering the throttle on a speeding car isn't stuck. It's being pressed harder, quietly accelerating our cosmic fate. The implications are staggering. If dark energy grows stronger over time, we could be heading toward a big rip, where galaxies, stars, and even atoms are torn apart in a violent crescendo of expansion. Alternatively, if it weakens or flips sign, the universe might collapse back into a big crunch, reversing 14 billion years of history in a fiery collapse. The CMB can't predict these scenarios outright. It's a snapshot of the infant universe after all, but its data, combined with other observations, acts like a cosmic seismograph picking up tremors in dark energy's behavior. Yet the plot thickens. Some theorists argue these anomalies aren't dark energy at all, but evidence of a crack in general relativity's framework. Could gravity itself weaken over vast distances, mimicking the effects of a changing dark energy? Others propose even wilder ideas, like dark energy interacting with dark matter, an invisible tug of war shaping the cosmos behind the scenes. The real challenge is untangling these possibilities. The CMB's signal is ancient, while dark energy's influence is strongest in the relatively recent universe. Bridging that gap requires piecing together disparate clues like a detective reconstructing a crime from century-old fingerprints. Future missions like the Euclid Space Telescope or the Vera Rubin Observatory aim to sharpen the picture, hunting for minute shifts in how dark energy sculpts the cosmos over billions of years. What makes this search so urgent isn't just the cosmic stakes, it's the irony. Dark energy makes up nearly 70% of the universe's energy budget, yet we know almost nothing about it. The CMB's whispers might be our best shot at decoding its secrets before the universe expands them out of view. And that's the real mystery, not just how the story ends, but whether we'll ever get to read the final page. Neutrinos are the universe's most elusive ghost particles, so light and slippery they pass through entire planets like they're not even there. Yet these cosmic specters may have left a faint fingerprint in the cosmic microwave background, imprinted at a time when the universe was a mere toddler. The CMB's subtle fluctuations don't just map temperature variations. They also encode the gravitational tug of war between matter and radiation in the early cosmos. And neutrinos, despite their diminutive mass, played a surprisingly pivotal role in that dance. Their presence altered how matter clumped together, leaving a signature we can still read in the CMB's statistical patterns today. For decades, physicists assumed neutrinos were massless, zipping through space at the speed of light. But experiments eventually proved they do have mass, just staggeringly small, millions of times lighter than electrons. The CMB allows us to weigh them indirectly. By analyzing how much they suppress the growth of cosmic structures, scientists estimate the combined mass of all three known neutrino flavors can't exceed about 0.12 electron volts, a whisper of weight on the quantum scale. But here's where things get strange. Some cosmological datasets, when combined with the CMB, hint at values slightly higher than lab experiments suggest. It's as if the universe is subtly disagreeing with our particle accelerators. Could this discrepancy point to something beyond the standard model? One tantalizing possibility is the existence of sterile neutrinos, a hypothetical fourth flavor that doesn't interact via the weak force like its known cousins. These shadowy particles would be even harder to detect but could contribute extra mass, throwing off the cosmic ledger. Another wild card: what if neutrinos don't behave as we expect in the early universe's extreme environments? Some theories propose they might have engaged in non-standard interactions, scattering off dark matter or decaying into unseen particles, altering their influence on the CMB in ways we're only beginning to model. The stakes are higher than they seem. Neutrino masses are tied to some of physics' biggest open questions, from why the universe has more matter than antimatter to the true nature of dark matter. If the CMB's anomalies hold up, they could crack open a window into realms beyond our current theories, but proving it won't be easy. Teasing neutrino effects from the CMB's sea of data is like listening for a single instrument in a symphony. Every note has to be perfectly isolated. Future experiments like CMB S4 or next-gen lab detectors may finally settle the debate. Until then, these ethereal particles remain both clues and conundrums, their secrets written in light from the dawn of time. The universe is supposed to be flat, not like a sheet of paper, but in the cosmic sense where parallel lines stay parallel forever, and the angles of a triangle add up to exactly 180 degrees. This perfect flatness is one of inflation theory's greatest triumphs, etched into the cosmic microwave background with mathematical precision. But what if we've been misreading the cosmic blueprint? A small but growing chorus of scientists is questioning whether the CMB's apparent flatness hides a subtle curve, a whisper of curvature so faint it's been lurking just beyond our instrument's grasp. Here's why this matters. The CMB's temperature fluctuations act like a cosmic ruler, measuring the universe's geometry on the largest scales. If space were positively curved like a giant sphere, hot and cold spots would appear larger than expected. Negative curvature, resembling a saddle, would make them seem smaller. Yet the CMB's patterns match neither. They align perfectly with flatness, down to a margin of error around 0.2%. That's like measuring the length of a football field and being off by less than the width of a single blade of grass. Inflation explains this by stretching the early universe so violently that any initial curvature was ironed out, leaving behind the smooth, flat cosmos we see. But cracks have started to appear in this tidy picture. Some analyses of Planck satellite data suggest the CMB's fluctuations might not be perfectly isotropic. They appear slightly smaller in one hemisphere, a possible telltale of negative curvature. Other studies argue that when combined with measurements of galaxy clustering, the data favors a closed universe at roughly the 3 sigma level, a statistical nudge just strong enough to raise eyebrows. It's as if the universe handed us a perfectly flat puzzle, only for a few edge pieces to refuse to fit. Skeptics are quick to point out the flaws. The statistical significance is borderline, and systematic errors like foreground dust or calibration quirks could mimic curvature. There's also the cosmic variance problem. We only have one universe to observe, and its largest scales might simply look peculiar by chance. Imagine flipping a coin 10 times and getting 8 heads. It might feel meaningful, but it's still within the realm of randomness. Yet if the curve is real, the implications are seismic. Inflation might need a radical rewrite. Perhaps it didn't last as long, or didn't stretch space as thoroughly as we thought. Some theorists propose multi-stage inflation, where brief pauses in expansion left residual curvature imprinted. Others wonder if dark energy's acceleration could be warping space-time in ways that masquerade as curvature. The most tantalizing possibility, that we're seeing evidence of a finite universe, one where space loops back on itself like a video game map. A positively curved cosmos could be finite yet unbounded, meaning if you traveled far enough in one direction, you'd eventually return where you started. It's a poetic idea, one that transforms the universe from an endless void into something more intimate, a cosmic not tied by the Big Bang itself. The curvature controversy isn't just about geometry, it's a battle for the soul of cosmology. Either we're living in a razor-flat universe, exactly as inflation predicts, or we're on the verge of discovering that space-time has a gentle bend, a curve that could unravel our most cherished theories. For now, the CMB keeps its secrets close, But as telescopes grow sharper and models more refined, we might finally learn whether the universe plays by Euclidean rules or if it's been bending them all along. What if dark energy isn't just a modern cosmic phenomenon? What if it had a brief, dramatic cameo in the universe's earliest moments? That's the radical idea behind early dark energy, a hypothetical phase where dark energy surged and vanished like a cosmic flash in the pan, long before the CMB's light was set free. Proponents argue this fleeting burst could solve some of the CMB's thorniest puzzles, from the Hubble tension to anomalies in large-scale structure. But here's the catch: if early dark energy existed, it would have left behind a universe subtly, but unmistakably, different from the one our textbooks describe. Picture the universe in its first 100,000 years, a seething plasma of particles and radiation. According to standard cosmology, dark energy was negligible then, a silent spectator to gravity's dominance. But early dark energy flips that script. In this scenario, a short-lived dark energy field briefly accelerated the universe's expansion during this epoch, then decayed away before recombination. Think of it like pressing the gas pedal for just a split second during a long road trip, enough to alter your speed at the time, but leaving no trace once you've coasted back to cruising velocity. How does this solve the Hubble tension? By tweaking the cosmic expansion rate in those critical early moments, early dark energy would change how we extrapolate from the CMB to today's universe. Measurements based on the CMB assume a steady expansion history, but if there was an extra speed boost early on, it would make the present-day universe appear to expand faster, matching the higher values from supernova and galaxy observations. It's like realizing your car's odometer was calibrated after a hidden sprint at the start of the journey. Suddenly, the numbers make sense, but early dark energy's fingerprints wouldn't stop there. The same rapid expansion would leave imprints in the CMB's polarization patterns and the distribution of galaxies. Some models predict it would amplify certain acoustic oscillations, the universe's primordial sound waves, while suppressing others, creating a distinct signature in the clustering of matter. The trouble is, current data walks a tightrope. Some CMB anomalies hint at these effects, but none definitively confirm them. It's as if the universe left behind a smudged fingerprint, enough to suspect an intruder, but not enough to ID them. Critics aren't sold. Adding an entire new phase of cosmic evolution just to fix one discrepancy feels, to some, like over-engineering. Others point out that early dark energy risks creating new problems, like exacerbating the sigma-8 tension, a separate clash between CMB predictions and galaxy survey measurements. It's the cosmological equivalent of patching one leak only to spring another. And then there's Occam's razor. Do we really need an invisible, vanishing energy field, or are we missing something simpler about dark energy's true nature? Yet the theory's boldness is also its appeal. If early dark energy is real, it would mean the cosmos has lived through multiple eras of acceleration, first a blip, then the sustained push we see today. That raises even wilder questions. Could dark energy come and go in cycles? Is today's acceleration just another temporary surge? The CMB might not have all the answers, but it's the closest thing we have to a time machine for testing these ideas. Future experiments like next-generation CMB observatories or precision measurements of galaxy clustering could finally catch this phantom energy in the act. Until then, early dark energy remains a tantalizing what-if, a reminder that the universe's first chapters might be stranger than we ever imagined. Scattered across the cosmos like cosmic sinkholes, massive voids, regions hundreds of millions of light-years wide containing almost no galaxies, stretch the fabric of space-time into bizarre, empty expanses. But these aren't just passive gaps in the universe's structure. Some appear to cast shadows on the cosmic microwave background, creating subtle dips in temperature that challenge our assumptions about how evenly matter spread after the Big Bang. It's as if the universe didn't just expand, it left behind bubbles of nothingness so vast they warp the oldest light we can see. the connection between voids and CMB anomalies isn't obvious at first glance. According to general relativity, when light passes through a massive structure like a galaxy cluster, it gains energy climbing out of the gravitational well, then loses it falling back in a wash that leaves its temperature unchanged. But voids flip this script. Photons entering these empty regions lose energy as the universe expands beneath them, then fail to fully regain it upon exiting, creating a net cooling effect known as the integrated Sachs-Wolf effect. The result, cold spots in the CMB that align eerily with the locations of the largest known voids. Here's where it gets controversial. While some of these alignments could be coincidental, a handful, like the notorious cold spot, defy easy explanation. One particularly striking void complex, dubbed the Eridanus supervoid, spans nearly 2 billion light-years and coincides with one of the CMB's most pronounced temperature dips. Statistically, the odds of such a perfect overlap happening by chance are slim. Could this be evidence that our universe isn't as homogeneous as we've assumed? The standard cosmological model relies on the Copernican principle, the idea that no place in the universe is special and matter is distributed evenly at the largest scales. But if voids consistently imprint cold spots on the CMB, it might mean the cosmos has hidden pockets of imbalance, regions where the density of matter varies dramatically. Some theorists suggest these voids could be remnants of colossal quantum fluctuations frozen into spacetime during inflation, like air bubbles trapped in ice. Others propose even wilder ideas. What if we're seeing the shadow of a parallel universe pressing against ours, or the gravitational aftershock of a long-ago collision between cosmic membranes in the multiverse? Skeptics counter that voids might not be the culprits at all. The cooling effect they produce is subtle, and some calculations suggest even the Eridanus supervoid shouldn't create a cold spot as dramatic as the one observed. Could there be unknown physics at play, perhaps a mysterious interaction between dark energy and these vast empty regions? Or might the voids themselves be less empty than they appear, hiding diffuse clouds of dark matter or exotic particles that amplify their gravitational influence? The most tantalizing possibility is that these voids are windows into a deeper cosmic truth. If their influence on the CMB holds up under scrutiny, we might need to rethink not just the universe's structure, but its very origins. After all, if inflation didn't smooth out space as thoroughly as we thought, what else might it have left behind? The void's cold whispers could be clues to forces that shaped reality before the first stars flickered to life, a reminder that sometimes the universe speaks loudest through its silences. What if the universe's very first black holes weren't born from dying stars, but from the chaotic pressures of the Big Bang itself? This wild idea, known as primordial black holes, suggests that in the furnace of the early cosmos, dense knots of matter could have collapsed directly into black holes, no stars required. And here's where the cosmic microwave background enters the story. If these ancient gravitational traps exist, their fingerprints might be hiding in the CMB's faintest fluctuations, not as dark smudges, but as subtle distortions in the very fabric of the universe's oldest light. Think of primordial black holes as cosmic fossils, relics from an era before atoms or even protons had fully formed. Unlike their stellar counterparts, these wouldn't be the products of collapsing stars. Instead, they'd be forged from raw density variations in the infant universe regions where space was so tightly crunched that gravity overwhelmed all other forces. The CMB offers a way to test this. As these black holes formed, their intense gravitational pull would have warped the surrounding plasma, leaving telltale imprints in the CMB's temperature and polarization patterns. It's like finding dinosaur footprints in a layer of mud. The shape and depth reveal the creature's size and weight, even if it's long gone. The implications are staggering. If primordial black holes are out there, they could solve one of cosmology's biggest riddles, the nature of dark matter. Unlike exotic particles, which remain frustratingly elusive in lab experiments, black holes are gravity-incarnate objects we already know exist. Some models suggest these primordial variants could range in size from asteroids to moons, collectively accounting for the invisible mass holding galaxies together. The CMB could be our best shot at spotting them, since their clustering would alter how matter was distributed during recombination, subtly changing the statistical texture of the CMB's fluctuations. But there's a plot twist. Not all primordial black hole theories fit the data. If too many of them formed in the early universe, their intense gravity would have disrupted the CMB's delicate temperature variations in ways we don't observe. Some versions of inflation, however, predict just the right number sparse enough to avoid wrecking the CMB's smoothness, yet abundant enough to explain dark matter's grip on the cosmos. It's a cosmic Goldilocks problem. Too many, and the CMB would look scrambled. Too few, and they'd be irrelevant. The sweet spot, black holes with masses between 10 to 1,000 times that of our Sun, lurking in the cosmic shadows. Yet the CMB isn't the only clue. Gravitational wave detectors like LIGO have picked up mergers of surprisingly hefty black holes, some far larger than stellar collapse should allow. Could these be primordial stragglers finally colliding after billions of years? The timing lines up eerily, but proving it requires connecting the dots back to the CMB's primordial whisper. Future observatories like the Laser Interferometer Space Antenna might catch these black holes in the act, while next-gen CMB telescopes hunt for their statistical ghosts in the ancient light. The most tantalizing possibility, that primordial black holes aren't just dark matter, they're cosmic time capsules, preserving secrets from before the first stars. If inflation birthed them, their distribution could reveal quantum ripples from the universe's first moments. Some theories even suggest these black holes might contain hidden universes of their own, their singularities birthing new spacetime like cosmic Russian dolls. For now, the CMB keeps its secrets, but every anomalous fluctuation, every unexpected alignment, could be a breadcrumb leading us closer to uncovering the universe's original black holes and rewriting the story of dark matter in the process. The hunt isn't just about finding missing mass, it's about peering into a past so distant even light barely remembers. Among the most tantalizing what-ifs in physics is the magnetic monopole, a hypothetical particle that carries just a single magnetic charge, either north or south, unlike the inseparable poles we know in ordinary magnets. If these elusive entities exist, they'd be more than cosmic oddities. They'd be smoking guns for grand unified theories, the holy grail of physics seeking to merge electromagnetism with the strong and weak nuclear forces. And here's the twist: the cosmic microwave background might be silently recording their legacy, not as direct detections, but as shadows cast across the universe's oldest light. The hunt for monopoles begins in the early universe's unimaginable heat. Grand unified theories predict that as the cosmos cooled after the Big Bang, phase transitions, like water freezing into ice, rippled through space-time, creating topological defects where the fabric of reality kinked. These defects could have birthed monopoles in abundance, with masses a quadrillion times heavier than a proton. Inflation likely diluted their numbers, but if even a handful survived, their interactions with the primordial plasma would have left scars in the CMB. Imagine dragging a magnet through a cloud of charged particles. The disturbances would ripple outward, subtly altering how matter clumped together, and those imprints could linger in the CMB's statistical patterns. But there's a catch. Monopoles wouldn't just passively distort the CMB, they'd also catalyze proton decay, a process where matter unravels at their touch. If monopoles were plentiful enough, their proton destruction would have flooded the early universe with extra radiation, leaving a distinct bump in the CMB's blackbody spectrum. The absence of such a bump doesn't rule out monopoles entirely. It just suggests they're vanishingly rare, perhaps one per volume of space larger than our entire galaxy. That's a needle in a cosmic haystack, but the CMB's silence isn't a dead end. It's a boundary telling us monopoles must either be heavier or rarer than our boldest theories predicted. Yet the story doesn't end there. Some models propose monopoles didn't form during grand unification but emerged later as relics of other exotic phase transitions. These light monopoles, with masses mere trillions of times a proton's, could have avoided overproducing radiation while still leaving gravitational wrinkles in the CMB. Others speculate monopoles might cluster in cosmic strings, thread-like defects stretching across the universe, acting as hidden anchors that warp space-time in ways detectable through CMB lensing. It's like searching for invisible strings by watching how they bend the light passing through them. The most electrifying possibility: monopoles might not be particles at all, but fleeting disturbances in quantum fields, appearing and vanishing too quickly to leave traditional traces. In this scenario, their shadows in the CMB wouldn't be from direct interactions but from cascading effects like echoes of a shout no one heard. Future CMB experiments with unprecedented sensitivity to polarization and spectral distortions might finally catch these whispers. Until then, the monopole hunt remains a testament to the CMB's power. Even in what we don't see, the universe is speaking. The idea of parallel universes colliding with ours sounds like pure science fiction, until you stare into the cosmic microwave background and wonder if it's leaving us clues. Take the infamous cold spot, that billion-light, year-wide anomaly where temperatures plunge unexpectedly. Could this be a cosmic bruise, a dent in our universe's fabric left by a glancing blow from another bubble universe in the multiverse? The concept isn't as far-fetched as it seems. If the multiverse exists with countless universes bubbling up like foam in an endless cosmic sea, occasional collisions would be inevitable. And the aftermath might just be frozen into the CMB's ancient light. Picture it like this. Imagine two soap bubbles floating in air, gently touching. Where they meet, their surfaces deform slightly, creating a dimple. Now scale that up to universes. In the chaotic frenzy of eternal inflation, the theory that our universe is just one expanding pocket in a vast multiverse nearby bubble universes could have bumped into ours during its fiery infancy. That collision would release energy, distort spacetime, and leave behind a telltale temperature dip in the CMB. The cold spot fits that description eerily well, a vast circular region of cooling, as if something enormous once pressed against our cosmos and left a mark. But here's where things get thorny. While the multiverse explanation is dazzling, it's also notoriously hard to test. Other universes, by definition, lie beyond our observable horizon, leaving us with only indirect traces like shadows on the CMB. Some simulations suggest such collisions would produce more than just cold spots. They'd also generate swirling polarization patterns in the CMB's light, like fingerprints in wet clay. Yet searches for these telltale spirals have come up empty so far. Skeptics argue that the cold spot could just be a statistical fluke, a cosmic roll of the dice that happened to land on an improbable number. After all, with trillions of possible fluctuations in the CMB, a few anomalies are bound to look suspicious. Then there's the problem of alternatives. The cold spot might not need a multiverse to explain it. It could be a supervoid, a vast, empty region of space whose gravitational pull subtly cools passing light. Or perhaps it's a rare knot in spacetime itself, a relic of quantum fluctuations from the universe's first moments. Even more unsettling, what if our understanding of cosmic inflation is incomplete, and the cold spot is a sign that the early universe didn't expand as smoothly as we thought? The multiverse might be the sexiest explanation, but it's far from the only one. Yet the allure of the multiverse theory isn't just in its grandeur, it's in its predictions. If bubble collisions are real, they wouldn't just leave one cold spot. They'd create many, scattered across the sky like scars. Future CMB experiments, like the upcoming CMB S4 project, could scan for these patterns with unprecedented precision. turning the cosmos into a detective's chalkboard. A single definitive imprint could rewrite our understanding of reality. For now, the cold spot remains a riddle wrapped in a mystery. It dares us to dream bigger, to consider that our universe might not be alone, that beyond the edges of our perception, other realities may have once brushed against ours, leaving faint echoes in the oldest light we can see. Whether those echoes are real or just cosmic static, they remind us that the universe's greatest secrets often hide in plain sight. Could the laws of physics be changing, not just across space but across time itself? Hidden in the cosmic microwave background might be clues that fundamental constants, those unchanging numbers governing reality, aren't so constant after all. Take the fine structure constant, symbolized by alpha, a value so precise it dictates how light interacts with matter, how stars burn, even how molecules form. For decades, we've assumed alpha never wavers, but what if it did? The CMB, as a fossil of the universe's infancy, could reveal shifts in alpha's value over billions of years, rewriting not just cosmology but the very foundations of physics. Here's how this cosmic detective story unfolds. When the CMB's light broke free 380,000 years after the Big Bang, its spectrum was imprinted with the fingerprints of atomic interactions, absorption lines where elements like hydrogen and helium soaked up specific wavelengths. The precise positions of these lines depend critically on alpha's value. If alpha were different in the early universe, those lines would shift subtly, like a song played at the wrong speed. By comparing the CMB's spectral fingerprints to lab measurements today, scientists hunt for discrepancies that might betray a drifting constant. The implications are staggering. If alpha varied, it would mean the universe's rulebook isn't written in permanent ink. Some theories, like string theory, actually predict this, suggesting extra dimensions could cause constants to fluctuate as the cosmos expands. Others propose more radical ideas. What if the speed of light or the strength of gravity also shifted, leaving traces in the CMB's polarization or temperature patterns? It's like discovering the markings on a ruler change depending on when you use it, but the data teases more than it confirms. Some studies of quasar absorption lines, light filtered through ancient gas clouds, hint that alpha might have been slightly smaller billions of years ago. Translating that to the CMB is tricky, though. The Planck satellite's measurements are precise enough to constrain alpha's drift to a hair's breadth, but not to zero. The numbers hover tantalizingly close to no change, yet with just enough wiggle room to keep theorists awake at night. Critics argue these anomalies could be observational ghosts. The CMB's light has traversed 14 billion years of expanding space, passing through galaxy clusters and magnetic fields that might mimic a shifting alpha. Even tiny errors in subtracting foreground interference could create false signals. It's like trying to measure a candle's flicker while standing in a hurricane. Yet the possibility lingers like a scent on the wind. If constants do vary, the consequences would ripple through everything. Stars might burn differently in distant epochs. The nuclear forces binding atoms could weaken or strengthen over time. The CMB becomes more than a relic. It's a time capsule holding a universe where physics itself evolves. Future telescopes, like the next-generation CMB observatories or precision atomic clocks in space, could finally settle the debate. Until then, the CMB's silent testimony keeps us wondering, are the laws of nature truly eternal, or do they dance to a rhythm we've yet to hear? What if the universe's quirks aren't glitches but artifacts? The cosmic microwave background's oddities, from its pixel-like fluctuations to its puzzling symmetries, have led some to wonder, could these be the telltale signs of a simulated reality? It sounds like sci-fi, but the idea isn't just whimsy. It's a serious, if speculative, frontier in physics. If our universe were running on some cosmic computer, the CMB might be where the code shows its seams. Think of it like a video game. Even the most advanced graphics have limits. Textures get blurry up close, shadows glitch at certain angles. The CMB's temperature variations, when mapped, resemble a grid of pixels with fluctuations oddly aligned like a rendered image. Could this be evidence of a finite resolution, a computational constraint baked into the fabric of reality? Some theorists argue that if the universe is a simulation, its processing power wouldn't be infinite. Just as a game engine approximates physics to save resources, a simulated cosmos might cut corners at the largest scales, leaving behind statistical fingerprints in the CMB's structure. Then there's the universe's eerie efficiency. The CMB's fluctuations follow a pattern so mathematically pristine, it's as if they were algorithmically generated. Inflation's near-perfect Gaussian randomness, the very thing that makes the cosmos feel natural, could also be read as the output of a finely tuned pseudorandom number generator. Even the anomalies we've discussed, the cold spots, the axis of evil, might not be bugs but deliberate Easter eggs left by the programmers. After all, what better place to hide a signature than in the background radiation of everything? But before we rewrite cosmology as a lines of code, there's the skeptic's counterpunch. The pixelation effect could just be how quantum fluctuations behave at cosmic scales, no simulation required. The universe's mathematical elegance might simply reflect nature's underlying laws, not a programmer's preferences. And let's not forget Occam's razor. Positing an entire simulated reality to explain CMB anomalies is like building a time machine to account for a missing sock. Yet the simulation hypothesis isn't entirely untestable. Some physicists propose that if the universe is digital, there should be fundamental limits to how finely space, time, or energy can be divided, like a cosmic frame rate. Others suggest hunting for overflow errors in high-energy particle collisions, where the simulation might briefly falter under extreme calculations. The CMB, with its quantum scale imprints, could be the ultimate debug log if we learn how to read it. Whether you buy the simulation idea or not, it serves a deeper purpose. The CMB's mysteries force us to question reality's scaffolding, to wonder if the universe is more malleable or more coded than we ever imagined. After all, the greatest scientific revolutions didn't come from accepting the world as it seems, but from daring to ask, what if it's not? And that's the real power of the CMB. It's not just a snapshot of the past, it's a mirror reflecting our boldest questions back at us. What if the Big Bang wasn't the beginning, just a violent reboot in an endless cycle of cosmic death and rebirth? Hidden in the faint whispers of the cosmic microwave background, some theorists believe there could be echoes of a universe that existed before ours, traces of an era so ancient even time itself might not remember. The idea of a pre-Big Bang cosmos isn't just philosophical musing. It's a daring challenge to our understanding of reality, and the CMB might hold the key to proving it. Think of the universe like a palimpsest, an ancient parchment scraped clean and rewritten. Even when the old text is erased, faint imprints linger beneath the surface. If a previous universe existed, its gravitational scars or quantum fluctuations could have survived the Big Bang's firestorm, subtly warping the CMB's patterns in ways we're only beginning to decode. Some models of cyclic cosmology, like Roger Penrose's conformal cyclic cosmology, suggest that black holes from a prior universe could have evaporated into radiation, leaving behind faint circular imprints called Hawking points in the CMB's temperature map. These would be cosmic fingerprints, evidence of a past we weren't supposed to see. The hunt for these relics is like searching for shadows in a thunderstorm. Current telescopes lack the precision to isolate such faint signals from the CMB's noise, but future observatories like CMB-S4 or space-based interferometers could change that. If a prior universe left behind any statistical anomalies, unusual correlations in temperature fluctuations, or unexpected polarization spirals, they'd be the smoking gun for a cosmos that's far older than we imagine. Yet skeptics argue that inflation, the universe's explosive early growth, should have erased any pre-Big Bang traces like a cosmic etch-a-sketch. If space expanded faster than light, how could anything from before survive? Unless, of course, inflation wasn't the universal reset we thought. Some theories propose that certain quantum fields or topological defects could have tunneled through the Big Bang, carrying information across the void like cosmic telegrams. It's a long shot, but in a universe full of surprises, ruling it out would be premature. The most tantalizing possibility isn't just finding evidence of a past universe, it's realizing our cosmos is part of something far grander. If the CMB ever reveals these ghosts, it won't just rewrite history, it'll redefine eternity. Until then, the silence of the ancient light keeps us wondering, are we the first chapter or merely a footnote in an endless story? From the eerie cold spot stretching a billion light-years wide to the unsettling alignment of the axis of evil, the cosmic microwave background is more than just ancient light. It's a cosmic detective story with 25 unsolved mysteries. Each anomaly, from the missing large-scale anisotropies to the whispers of non-Gaussianity, isn't just a puzzle. It's a catalyst pushing scientists to tear up old theories and imagine bold new ones. Think about it, without the Hubble tension's stubborn discrepancy, would we be questioning dark energy's nature? Without the lithium deficit, would we be digging deeper into the nuclear alchemy of the Big Bang? These aren't just gaps in our knowledge, they're invitations to rediscover the universe. Take the hunt for primordial black holes. What started as a wild idea to explain dark matter has now become a serious frontier, with gravitational wave detectors and CMB telescopes scouring the data for clues. Or consider the spectral distortions, those tiny bumps in the CMB's perfect blackbody curve. That could rewrite the timeline of cosmic evolution. Even the simplest assumption, like the universe's perfect flatness, is now under scrutiny, with some daring to ask, what if space-time has a gentle curve we've missed? Every mystery is a thread, and pulling on one could unravel everything we think we know. What makes these enigmas so thrilling isn't just their complexity, it's their humility. The CMB reminds us that for all our advancements, the universe still holds cards close to its chest. The cold spot might be a supervoid or a collision with another universe. The missing B modes could mean inflation was quieter than we thought, or that it never happened at all. Even the simulation hypothesis, as wild as it sounds, forces us to ask, what if the rules we take for granted are just lines of code in a deeper reality? So here's the real question: which of these 25 mysteries grips you the most? Is it the phantom pull of dark flow, hinting at unseen giants beyond our cosmic horizon? The haunting possibility that constants like alpha aren't so constant after all? Or the spine-tingling thought that the Big Bang wasn't the beginning, just a reboot in an endless cycle? Drop your pick in the comments. We're all detectives in this grand cosmic mystery. And if you're hungry for more deep dives into the universe's greatest secrets, hit subscribe. The cosmos has only begun to whisper its secrets, and the next revelation could be just around the corner.